Okay, so welcome back to another lecture of E2080 Microprocessor Systems Design and Interfacing. So we have completed our lectures on the building of our own 8-bit microcomputer. And I hope all of you are enjoying the lab sessions, the virtual lab sessions where you're trying to build your own 8-bit microcomputer using Logisim. So my suggestion is like thoroughly do changes to that based on whatever the framework that I have given. Play with the control unit, improve the functionalities and see what all you can do with that, because that understanding will take you a long way in understanding of a very complex microprocessor as well. So from today onwards, we are going to discuss the real architecture, the real importance of a microprocessor. We slowly start with our own architecture, more importance to the architectural part of the microprocessor. Then we will slowly discuss about how to communicate. In fact, before that, we discuss about the software aspects of a microprocessor. So first will be the hardware aspect, then will be the software aspect. Once we understand that, we will slowly start to look outside. Look outside means the environment. So we need to have the interfacing, right? So that's the concept. The topic, the course title also actually says that. Design means it's all about the architectural and the software design. And then of course, once everything is understood well, then of course a use of a microprocessor system is all when it communicates with the outside world, right? And that's where the interfacing aspect comes into the picture. Okay, so with that, let's start. Okay, so first, the very first official definition of microprocessor. We discussed about this a lot in the previous lectures, but now let's do it in a very official way. Okay, so let me use the pointer here. Okay, so just to put it in a very nutshell or a very high level picture, we do have the most important part which does the operations for us. We could treat this as the sort of the main part which does the mathematical and the logical operations, the arithmetic and logical unit. So this is the crux part which does the functionality for you, right? And then of course there is very minimal memory. That is the important striking point. We do have a bank of registers. In our small 8-bit microcomputer, we talked about the register A, which is also known as the accumulator, and the register B. So we only had two registers, and then some small registers like the memory address register and the output register. So those are the register banks when I mean. But a modern day microprocessor that, for example, the Cortex M0 Plus microprocessor that you are going to learn, you do have a bunch of registers, something like 8 registers to play with. Okay, so that's what we mean by register bank. So this constitute the only memory available to the microprocessor unit. Okay, and then of course we do have the instruction fetching part and the instruction decoding or instruction execution part. This part, which is actually popularly known as the control unit, right? So this is basically nothing but your control unit. Don't get confused by that. So this is that digital circuit which forms the control unit. Okay, and then of course we do have the option to interface with the memory, the RAM that we had, right? That's not really part of any microprocessor. It should be coming outside of a microprocessor. So basically a microprocessor, what is it? It has an ALU, it has a certain bank of registers, and it has a control unit all on a single chip. Okay, so you will have a single chip, something like a single chip solution, right? The IC, the integrated circuit that we are talking about with some pin layout. And then inside of this, you do have an arithmetic logic unit, you have a control unit, and you have a bank of registers. Remember, there is no memory inside the chip. Okay, so that's it. So then as we discussed, the name micro is because it is all very large scale integration. That means the circuit is at a very small scale. Okay, so the chip will looks like extremely small, which you can see when you open up a laptop or a computer desktop motherboard. You can see that the microprocessor footprint is very small compared to the footprint of the motherboard, right? And then of course, just to coincide the names, it is at a very small footprint and it does the processing for you. And in fact, the processing is done by this guy. Okay, so the capability is in this guy. Okay, so yeah, official definition if you want to call it, it is a single processor core which has all these components, and it supports at least instruction fetching, decoding and execution. Okay, so this is the part, and in fact this part is done by the control unit, which you are aware by now. So this can be normally used for general purpose computing, okay, but needs to be supported. So this standalone will not help you in that general purpose computing that we talk about, because we need memory. So it needs to be supported with external memories and external input output interfacing. So you have to do that. So microprocessor doesn't have that option. It may have bare minimum the memory interface option, and then of course the interfacing with the outside world, the peripherals and all those things, and also the memories that you have to provide. That won't come in a microprocessor. So I hope that distinction you should be very clear with. Okay, so moving on. So that is microprocessor all about. Then we go to the microcontroller. Okay, so then microcontroller is again a single chip, but within that single chip you do have a microprocessor chip. Okay, so the microprocessor sits here. Then you do have the memory. You have the program memory and you have the data memory. They can be single or they can be separate. And then you have the bus. We already know what is a bus. And then of course you do have the interfacing option to the digital input output, the analog input output, the timer, the peripheral, other peripheral devices that you can think of. All these, the provision will be there. These devices won't be part of it, but the provision, the interfacing provision you will be giving. So microcontroller in fact is a single chip solution, and inside of that chip you do have a microprocessor system, you do have the memory options and you have the interfacing options. So that's what. So microprocessor plus memory and the interfacing option gives you the microcontroller. Okay. So that's it. So typically has a single processor core, but modern day systems doesn't restrict in that. You do have multi-core options in the case of a modern day microcontroller. And then of course it do have the memory blocks inside and the peripheral options given to you. Okay, typically, so what is the use? So we talked about microprocessor, the use could be a general computing solution. But in the case of a microcontroller, because it has a memory and all those aspects, typically it is used for control purpose, something like an embedded application. Okay, so that's one application. So do remember all these components again is on a single chip. So you do have a microprocessor with the memory plus the interfacing option plus the bus option on a single chip, it becomes a microcontroller. I hope I'm very clear cut in that definition. Okay. So going forward, then what is a microcomputer? So we talked about microprocessor, that is the smallest thing that you can think of. Then you add on to that memory and the peripheral options, it becomes a microcontroller. And then what is a microcomputer? The only difference between a microcontroller and a microcomputer is like microcontroller is a single chip where all the components are there, but microcomputer is not like that. It has a microprocessor chip, it will have the interfacing chip separate, it will have the memories chip separate, and then of course the interfacing we have to make it. And it may have buses which carry the address alone, which carry the data alone, and which carry the control bus alone. And in fact this is what we did in our 8-bit microcomputer, because we designed it using individual blocks, and they were having our own designs for all these things. It doesn't come as a single chip solution, and that is what the difference is all about. I hope it's very clear to you. The difference between if now onwards, this day onwards, if somebody asks you what is the difference between a microprocessor, a microcontroller and a microcomputer, even if you are sleeping, you should be able to answer this. I hope it's crystal clear. Now there is an interesting way. When the microcomputer or the microprocessor or in fact the microcontroller systems developed, people thought it as a single bus controlling both data and address. So those architectures were typically known as the von Neumann architecture. So please remember that. So you might come across this particular term many times if you are going to study in depth about the computer architecture. So von Neumann versus Harvard architecture. It's a very interesting concept. Very simple. Actually in von Neumann you don't have a separate data bus and a address bus. You do have the same bus. In fact our own 8-bit microcomputer that we designed is belonging to the von Neumann architecture, because we only have one bus for both the data transfer and the address transfer. Remember that instruction was also using the same bus and the data was also carried using the same bus. So that sort of architecture is known as von Neumann architecture. In fact that is where it all started. And then of course there are Harvard architectures where you do have separate bus for address, data and control. In fact control generally is a separate bus, you don't mess with that. So data and address, if you have a separate bus, it becomes a Harvard architecture. If it is the same bus, same set of wires, then it becomes a von Neumann architecture. So what is the advantage of having a Harvard architecture where you have a separate bus for address and data? You can speed up. Your instruction fetching is independent of your data fetching, right? So that means you can speed up the operation. So it will be much faster processes. So if you are looking at a much faster processing, most of the time its internal will be Harvard architecture. But then what is the disadvantage? Just pause and think, what is the disadvantage of having a separate address and separate data bus? Yes, the answer is too much of area occupancy, right? You need to have a separate layout for address bus, separate layout for data bus. That means your area footprint will be higher and even the power consumption will be higher, and that is not really great. So if you are looking at a lower footprint, mostly embedded sort of nature applications, you may go for a von Neumann architecture. But if you have a lot of space like in a typical workstations or server systems, you don't really worry about the power or the area footprint, then you go for a Harvard architecture. So please beware that in mind. It's very simple, but it's very important concept. Okay, so I hope you understood the difference between a microprocessor, a microcomputer, and a microcontroller, and you also understood the difference between a Harvard architecture and a von Neumann architecture. Okay, so with that, let's move on. Let's slightly go more important towards application side. Embedded systems. This is not really part of our course, but you may be taking this course in future. So what is an embedded system and why add a computer to a larger system? So these two things are very important. So embedded systems, the picture, as I said, a picture is worth 1,000 words, right? So you can see it. Camera is an embedded system. The modern day cars are classic examples of embedded system. A printer, the printer that we have, for example, the fax scan copy machine that we have in our days now, I mean in our houses nowadays, most of the houses have their own computer and printer systems, right? So that itself is an embedded system. Modern day speakers, the wireless Bluetooth speakers from Bose and related companies are embedded systems because they do a lot of things inside. The Echoes, Amazon Echoes, for example, is an embedded system. The mobile phone, of course, is a classic example of an embedded system. Of course, there is a fine line, because we discussed about this during one of the lectures previously. There's a fine line for a smartphone because it does a lot of things. So some people can argue that it's not really an embedded system. It is slowly going towards a general purpose computing system because it does support the calling operation. It does support the camera operation. It may have the provision to measure your heart rate. It has the provision to maybe do lot more other processing capability. It is like a mini computer nowadays. So is it really an embedded systems? Yeah, it's a fine line. It's a very difficult answer, but yeah, let's treat it because of these capabilities. So most of the time, this is not a strict definition, but it's easy to actually have a definition, or it's important to have a definition actually. So it is an application specific computer system. So you may be targeting one or two specific applications. It's not like a general purpose laptop or a general purpose workstation. It does have an application. Okay. It is generally built into a larger system. So embedded system will form part of a larger system. Okay. So embedded systems, for example, in car you will have maybe many embedded systems. It's not just one embedded system. Okay. So for example, I can take an example. So the airbag system in a car. So that itself is an embedded system because it has a specific application, it has a specific circuitry, and it is actually something very important part, right? So it is part of a bigger system. So even inside a car, you can find a smaller system which is an embedded system. So that's very important. So I hope you understand this point, you understand this point. This is the point which we didn't discuss earlier. So embedded system has this is very important. It has the constraint of real-time operation. So for example, airbag is a classic example where you have to be real time, right? The accident comes, the airbag has to trigger. Otherwise, the entire meaning of having an airbag is spoiled. So very important. So it's a real time constraint is there. So that makes it, so if somebody asks you to define an embedded system, I think this is a very interesting 3 points. It is application specific. It is a subsystem part of a bigger system. And of course, it has to be real time. And then of course we already know why we want to have a microprocessor or a microcontroller to be part of an embedded system, because it will, I think more than all these points listed out, I think the single key point that I would like to put across is that flexibility is that programmability, is that ability to completely change the functionality of the circuit. That is why you need a microprocessor or a microcontroller or in fact a microcomputer to be part of your embedded system. And of course, if you want to again put a block diagram sort of thing, you do have input from the environment, that is a sensing part. You do have the embedded computer which has a software and the hardware part. You have the user interface and link to other systems, because as we said, it is part of a bigger system. So you should have the provision to interface with other embedded system. And then of course some user interface, some human machine interface to control it, right? Sometimes you need to program it, sometimes you need to set it, sometimes you need to view the output, right? You have the dashboard on your car, which is like the interface to the human, right? Human is having some sort of feedback, right? Sort of open loop feedback, you can say. So something there. So that interface should be there. And then of course, it will have an actuator, and with, for example, the airbag system that we discussed about. The actuation is the triggering of the airbag, right? So it senses the speed and it senses the tension on your seat belt. So those are the sensing which is going on to the airbag embedded system, and then the actuation is the triggering of that airbag. Okay, so that's one classic example I can take. So I hope it's clear. So again, if somebody asks you what is an embedded system, you should be crystal clear and telling you, okay, let me ask you these questions. Is it an application specific system? Is it part of a bigger system? Those are lighter constraints, I would say, but the bigger constraint is it real time? Is it real time? Very, very important, right? If it is satisfying all these three, you can say safely that it is part of an embedded system. Okay. Then some examples, I think very easy for you to actually judge all this. You do have a bike, most of you, and you do have a bike computer or the dashboard, right, in front of you. So the major functionality for that is, this is application, it is used for speed and distance measurement, right? Constraints, of course, the size, you cannot have a big dashboard for a bike when you compare that for an aeroplane, right? You can't have that. Cost, yeah, the bike cost is in general lower than a car cost. So of course, no, I'm not talking about the Harley Davidsons or the bullets. I'm not talking about that. Of course, those costs may come to as close to a smaller car. But yeah, generally the cost is lower. So that is a constraint. Power and energy. Of course, the battery of a bike might be much lower than the battery of a car. So you are constrained by power and energy. And then weight, of course, you can understand this. So these are the constraints that you put. So these are the design constraints for you to come up with your embedded system. And then of course the inputs, the wheel rotation, that is the input that is used for the speed and distance measurement. And then of course the mode key, you may have a mode key, right, on your dashboard to change something like what is the current mileage, for example, or current distance covered, for example. So you use a mode key, and the output is the display, right? And then of course with these constraints, you can only afford maybe an 8-bit microprocessor system. You may not be able to afford a 32-bit microcomputer system, because those consume a lot of power, that may occupy a lot of area, and maybe performance also, you don't really need a 32-bit system. Okay, so that's it. So coming back to the previous block diagram, you can put it this way: you have the input and you have the output, and then of course this processor, which may be an 8-bit system, which will be sitting inside here and controlling that. Okay, I hope it's clear. And then going for another example, a bigger system, an engine control unit, the entire thing will change, and you can actually pause this video and see the bunch of sensing, bunch of embedded system options that is there in a modern day car. You will be amazed by the options. Within the engine itself, so much of sensing has to be done. Then of course at the driver's seat, at the wheel, so many, right? So many. You can just take your own car and see how much of sensing option is there inside that. So functions in a very brief way, we do have the options for fuel injection, air intake settings, spark timing, exhaust gas circulation, electronic throttle control, knock control, and all you electrical engineers will be thinking, what all nonsense is this? These are all mechanical things, but you need to, if you are going to work in a car company like Mercedes-Benz or Ford or Tata Motors or Mahindra, and you are part of the engineering electronics team there, you need to understand all this. And that is where I always say BTech electrical engineering is just a start, and it is an opportunity to talk to the entire world of interdisciplinary engineering, because you need to talk to the mechanical engineers, you need to talk to the civil engineers, you need to talk to the computer scientists, you need to talk to the physicists, chemistry people, maths people, and you need to have that opening up and communicate with them. So you really are an embedded system, right? Electrical engineering itself is an embedded system talking to the bigger world of engineering and sciences, right? So always think in that perspective. And in this case, the constraints, of course, reliability in harsh environment. We know the world of cars, and the cost. Of course, cost, you can't put a really high limit, particularly in a country like India. And then, of course, the weight also, right? And then inputs, many, we can't put it here. So many of them. Outputs, you already know, the dashboard and also network. Nowadays, you do have the connected car concept, so you will have that interfacing as well. And then, of course, in this case, we have a little bit luxury, and we may need a little bit luxury because of the safety critical aspects of many of these systems. So you do go for higher resolution and higher precision and higher accuracy. So you may go for a 32-bit with some internal memory with a higher speed of operation. So you need basically higher performance embedded system compared to that of a bike in the previous slide. Okay, I hope it's clear. Okay, so that's it, and we come to the last slide for this week. I'm relatively loading you less this week because we do have the importance of building your own 8-bit microcomputer. So please go back and spend a lot of time on that. And this is the last slide for the week. And this is a very, very important slide and a very, very critical slide, which maybe you may have to come back to this slide in future many, many times, wherever you are, if you're going to work in this world of electronics. So very interesting slide. Let's spend some time on this. Okay, I can make circuits, I can make systems purely based on discrete logic circuits. That's what you are going to do in lab also as part of your digital circuits lab, where you will be using discrete ICs, discrete logic ICs for building up circuits. So the design cost will be very low because individually the ICs are not very costly, and then unit cost is also maybe mid-level, you can say, because you will be using discrete components and maybe on a breadboard. But updates and bug fixes, very, very hard. Just think of using all the logic ICs on a breadboard and then wiring it up, and then if you want to, if you face a bug, debugging that is a very, very tedious part. And if you want to upgrade also, very difficult, right? You need to rewire everything. Size will be large because it's not like an optimized PCB layout, because you're building mostly on a breadboard sort of an environment. So obviously the size will be large. Weight will be high because of the discrete components and no optimization. Power will be difficult to say because it depends on the efficiency of you as a designer. How do you wire it up and so on. System speed will be very fast. There is no compromise on that. Then instead of using the discrete logic ICs, if you use a software like Cadence, maybe you are learning that in your CAD lab. So something like that, or some other software like let's say Xilinx, if you're working on an FPGA side, digital VLSI side, you may come up with application specific integrated circuit, and as the name suggests, instead of using discrete components, you are going to wire it up on a PCB. You are going to fabricate a PCB. So in that case, the design cost is high because it involves a lot of design aspects, the layout aspect, which is a very complex task. The unit cost will be very low because you are going to actually once you make that layout ready, it is just about making it up in very, very low cost, right? It's very easy. Just tap, you can make it. Then upgrades and fix, again very hard because once you make the layout, it's very difficult to debug in most of the time. Flexibility is very less. Upgrading will be tough because you need to go back to the design and redesign that. So size, of course, it's a sort of an integrated circuit. It's bound to be small. Weight also will be small. Power also will be small because you are fine tuning the circuit for that very specific application. So very, very high chance that your power consumption is extremely low. And they are very fast because it's optimized like that. You are going to optimize your PCB during your design so that the speed will be very fast. And then the programmability, as I said, is very limited. Here you may have to change the hardware, change the layout if you want to change the functionality. And that is where the programmable logic like FPGAs and programmable logic devices, nowadays nobody uses PLDs, but still they are used in all the processing systems in big companies and all. So field programmable gate arrays, which you will be very familiar after the digital circuits course. So the advantage here is you do have a lot of programmable aspects. Design cost, you might know it already, maybe it's low or mid based on the application. Unit cost also is mid, not as low cost as this, because FPGAs are costly, so it's somewhere mid. Upgrades and big bug fixes are very easy because it's mostly software controlled hardware, right, in this case. So it's not very difficult. Some people say that, yeah, Verilog debugging is very tough. Yeah, I agree to them, but much easier than that of an ASIC or a discrete logic. Size is smaller, not as small as this because it's not an optimized circuit. It takes the footprint of an FPGA, so it is not that extremely small. Weight will be smaller, lower, but not comparable to an ASIC. And power consumption is not as low as ASIC because it does consume, because the programmable logic obviously is programmable, so it is more power consuming than a dedicated circuit. System speed is also very fast. There's no problem there. But the biggest advantage I would say is like the programmability aspect. Okay, so you could say that these three belongs to the category of dedicated hardware, which means that you are dedicating it for a specific application. So that's a very important point. And then comes to the software running on a generic hardware sort of thing, comes the category of the microprocessor plus memory plus peripherals and the microcontroller. Okay, so those two systems which we discussed in the first few slides in this class, the design cost is low or low to mid, unit cost is also not much, upgrades and fixes are very easy, which you already should be able to understand that by now, right? Size, yeah, small to medium you can say. Weight is also low, power is also medium. And then of course system speed is not as high as dedicated circuit, but of course they are reasonable. Okay, so now this chart is very important because this clearly shows that if you are really for a single application, if you are really your requirement is for a single application with a very low power requirement, you may go for an ASIC. If your power requirement is relaxed, you may go for a programmable logic. But if your application, you envision that your functionality is going to change in future, you definitely have to go for a microprocessor or a microcontroller. I hope that distinction is very clear. And in this course, we will not be talking about ASICs or FPGAs. We only will be talking about microprocessor systems. Okay, so with that, I hope the journey is going to be exciting. So next class onwards, we are going back to treat microprocessor systems in detail or a microcomputer system in detail. And we will see there. Okay, so this will be next week. Okay, so till then, it's goodbye from my side. Thank you.